design for manufacturability now also affects both front end and back end of process. So let's look at what do we mean by front end and back end. Some of you might already remember from the earlier lecture, but let's just recap what do we mean by front end and back end first. So when you are fabricating any device on silicon, it may or may not be electronic type device, but let's assume in this case we have some electrically active structures that we are going to fabricate. So you take silicon and you are going to make some junctions, right? So that we have n-type silicon, and then we dope these regions, and then let's say we make a gate here, right? And then we coat it with oxide, right? So let's say we coat this layer with an oxide layer, okay? And then now once you coat it with the oxide layer, you want to connect this transistor to another transistor, right? So what we make are metal contacts, right? So you make metal contacts like this, and then further on you take these contacts to connect to either this layer or other layers, right? So this is one, and then we have another metal line here. Let's assume there is one more layer here, right? So there are multiple ways to do this, okay? This is just roughly what one could do. So now we have the devices on silicon, right? And then we have metal and dielectric on the top. So we mean by front end is the doping region and the critical active layer, and just below the contact and gate. This is called front end of the line, right? FEOL. And then all the metallization and the connectors that we do is called back end of line, okay? So these connectors are very important to connect various transistors. At the same time, FEOL is the front end of line, is what we use to actually define the transistors and so on. So there is a functional difference between these two, right? So back end is primarily interconnects, and front end is primarily your active devices. So this is functionally speaking, right? But then there is also some process related, right? So back end, the temperature need to be, right? So the temperature that you can operate should be less than 450 or 500 degrees C, right? And then front end, normally you can go around more than 1000 degrees C, right? Which is used for doping activation and so on. So with respect to temperature, you can have these two different bands, where less than 450 is your front end, back end, and then you can have more than 400, right? It could be greater than 400, and less than 1000 or 150 degrees C is your front end part, right? So your reliability depends on how good you take care of both of this, right? So front end primarily defined by active device fabrication, and the back end primarily dictates your interconnects, right? So let's just have a quick look at how the back end kind of helps you in addressing the reliability. So we saw non-recurring engineering costs, right? So how do we reduce that? So another way of reducing those engineering costs is by using reconfigurable vias. So we saw this multiple metal lines are, so this is all metal lines. So this is M0, let's say M1, M2, M3 and M4. So these metal layers are connected through this via, right? So this is also metal via, and if you want to reduce your cost in designing and fabricating this multiple device and circuit architectures, you keep some standard via configuration. In this case 1, 2, 3, right? So these 3 metal layers are standard via configuration. Okay, and now we have some layers that are reconfigurable. So by doing this, you only change your metal 3 to 4 via layer. So only by changing that particular metal via, you can reconfigure and then you can make circuits that you want. So what we have done now is, instead of changing the whole metal stack, you are only changing one intermediate layer, right? So this will allow you to reduce your cost of fabricating, or cost of releasing a new product or realizing a new device, right? It's not just the cost, but it's also reliability. So now you are not really changing all the metal layers and all the interconnects. You are only touching one layer. So this also tremendously improve your yield when you go from one device architecture to another device architecture, while keeping your backend or your interconnect architecture relatively stable and standard. Okay, this may or may not be possible in all the cases, but we try to explore if it is possible to maintain the standard architecture. So in this case, we have only one reconfigurable via. Maybe we can do 2 reconfigurable via in difficult cases, right? So it can be 2 immediate layers, or you can have strategically take different layers in order to define new architecture. So in this case, M1, M2 might be made reconfigurable, and 3 and 4 could be made reconfigurable. So the whole idea of this reconfigurable interconnect is to reduce your overhead in development and also keep your reliability and yield at the maximum level by not redeveloping processes for new device or circuit architectures. So there are various factors that contribute to yield alone, right? So yield is very important thing that will really affect your product cycle. So you are taking yield from various perspective. One is there is a random yield loss, right? Systematic yield loss, right? So these are two primary yield losses that you could see. Random yield loss, as we already saw earlier in DFM. So this could be from your particle interaction, right? So you can have random particles coming and settling onto your wafer or your structure that could really affect your circuit, right? So you have a certain configuration, and if particle comes and sits here, then you are having a short circuit, let's say, right? But now you have a via here which should be connected, and then if I have a particle that is sitting in this part, then you are making an open circuit instead of short. So it depends on the nature of the particle, whether it is insulating or conducting. Your particle interaction with your circuit will give you random yield. So you don't know where these particles are going to come and sit on your wafer or on your circuit, right? So that's why we call it as a random yield loss. The other type of yield loss is a systematic yield loss. So this is primarily coming from your process. So just to give you an example, if you are depositing using plasma process, so I have a deposition plasma, and this is my wafer, right? So ideally speaking, you have a uniform plasma, and you have material coming onto the wafer is also uniform. But it is possible that you are unable to create a uniform plasma on top of your wafer. So this will create a depletion of your radicals, right? So on the sides you have very low number of products. At the center you have high number of products, right? So if you do that, you will have very thin layer at the center, thick layer at the thin layer at the edge and thick layer at the center, right? I'm of course exaggerating here to show the difference. This can be anywhere between 10 to 15% if it is worse, right? Ideally you want to maintain it below 5% non-uniformity, but this is systematic. So you can see here this yield is very systematic. So if your target thickness is somewhere here, so you are over depositing here and then under depositing here. So if you target your maximum to this level, so if you reduce it, my overall thickness will come down, right? So in this case, if I'm going to optimize my thickness, okay, so I'm optimizing my thickness. Initially my thickness was here, but my yield thickness wants to be here. If that is the case, it's going to roll off like this. So now my only let's say yielding device are within this range, right? Below this is all very thin, I'm going to lose those devices. Unlike the previous one where I have yielded somewhere here, but I have a window, right? So window of devices where I was able to use it, but now you are reducing that window, right? So one need to take a call on how to optimize the thickness for certain applications. So again, the design should also give the process developers whether the certain thicknesses that you are proposing can be used with a certain variation, right? If the variation is plus minus 5%, so your corner simulation should help you to give a confidence even with this 5% variation or 10% variation, you should be able to get desired yield, right? So the systematic yield loss is because of process interaction. So process has a certain systematic repeatability in nature, right? So we saw the front end lithography related yield. This is primarily coming from difficulty in patterning these devices. And how do we address these problems that we saw earlier? Pattern density yield issue is something new that we are introducing here. We will see in few slides what do we mean by density dependent yield, right? So lithography also has density dependent phenomena, right, which what we call proximity effect. And there are other processes, for instance CMP process or dry etch process is also pattern dependent, right? In a dry etch process, what we call density dependent etch rate, right? So you have a structure like this, right, and you want to etch this feature. This is photoresist and this is silicon, and here you will have more amount of radicals to come and etch, while here you are depleted with radicals here because all of them are consumed. So the etch rate, right, between these two structures are going to be different, right? And this is again pattern density dependent. So this is also will affect your CMP and fill and everything as well. So pattern density is something very important. And the next yield issue is parametric, right? This is performance related. So we discussed about timing related issues, right? If the timing is not good and if the memory is not yielding the required performance, so those are all parametric yield losses. So that is again another form of yield, which is functional yield, right? So the others are mostly structural yield related issues. The other one becomes functional, and functional more often is affected by the structural variations that you get during processing. So just to give you few examples, I'm going to give you few examples where the origin of these various performance limiting issues, primarily coming from back end, right? So front end lithography we addressed that, but now let's look at back end related issues where we are looking at interconnects. So this is an ideal interconnect. So you have, let's say, metal N and metal N plus 1, right? And this is the via. So this is how you want it to be, right? But then after fabrication, you see something like this. You have a sloped sidewall. Okay, this is coming from dry edge. Okay, or patterning in particular. So you will create these sort of sidewalls, right? And this sidewall will give you a variation in width in your via, right? What is the effect of this? The effect of this is the conductivity, right? So your resistance is going to be higher compared to what you actually perceived it to be. Okay, so that is not the end of the story. So let's look at another thing. So this is again coming from patterning plus CMP, chemical mechanical polishing. So here only due to patterning. So here you can see you have sloped sidewall, but also you see this dishing, right? So this dishing is again a very characteristics of a CMP, right? When you polish, when you do over polish, it is going to create dishing, right? And this dishing is again going to reduce the total resistance that you actually get out of this particular via. And these are all structural changes that you get, right? Instead of a very simple via hole, you have tapered profile, and not just tapered profile, but you also have dishing. So this is all structurally one can study, but then the performance, how the performance is going to affect the performance in speed, right? Because your resistance is high, you need to spend more power in transmitting the data, and it will also end up in noise related issues as well, right? So it's not just a structural variation, but performance will also be affected. Okay, so the other minute things that I also want to notice is these sort of slanted sidewall while you are looking at a very sharp end, and this is again affecting your metal line resistivity, right? And the other important thing I would also like to highlight here is how you are going to address alignment issue. So I have metal N, and then we have metal N plus 1, right? So here we have one interconnect, right? But then the distance to the edge, let's say this is A and B. So A is definitely larger than B. So that means any misalignment that you have, right, left or right, connecting to M1 is less is highly tolerant compared to B. Okay, so in whatever direction. So you want to make sure that you give enough space, right, enough tolerance. When there is a misalignment, you still have enough metal overlap so that you can avoid open circuit. So in the same architecture, right, so what we can do is I get this, but now because of misalignment, right, so my metal layer has moved further away, and you might make a contact, but this is going to be a reliability issue here, right? So it is just matter of time where you will have a very large current field here, and electron migration can happen that could result in failure. Okay, so you want to make sure that metal layer overlap is taken care by applying right amount of clearance so that you avoid alignment issues. So the next issue is about filling, right? So I make a trench, I want to fill it with metal, right? So this is again a via or metal line connections that you are making. So this is the cross section that you see here. So after making it, I'm filling it this area with the metal. Okay, so now I see a dish here, right? And this is very severe dish, but anyway, I'm exaggerating this, but it's going to be a severe dish here, right? But then there is nothing much we have done from the design side or a process side, because this is what the designer gave to us, and then we just fabricated it. But making sure we don't want any metal here, right? We did some over etch, and then that has resulted in dishing. But now if you do a process aware design, you will add some dummy filling. So what this dummy filling will allow us to do is a complete planar CMP, because you are not going to do over etching here, because the metal distribution is equal, right? So this is something we also saw in CMP, that your metal filling area, right, metal density distribution density has to be uniform, so that your removal rates are uniform, right? And if you can put some dummy structures, you can achieve this. This is not only helping you to achieve CMP uniformity, this will also help you in etch uniformity as well, right? So when you have structures that are equally distributed and you don't allow regions where you have so much open space, where you have too much of radicals available for etch, and in other parts you are starved of these radicals, right? So you want to make sure that you have a clear balance. So this dummy fill allows you to do that. This is a very good method to neutralize the density, right, the filling density. So an isolated line, right, is always interesting structure to study, because isolated lines are very simple to fabricate, right? And when you have devices with varying pitch, then you put a certain restriction here. It should be of certain pitch, and this line and this space should be equal, and so on, right? But then if you ask any process engineer, it is easy to achieve a periodic pattern, right, with the required specification compared to an isolated line or isolated trench. The reason for that is the open space that you have. This open space is the reliability or process difficulty, where even the etch is going to be slightly hard, because you have faster etch in these portions, and if the isolated lines are not uniformly distributed, you will have etch depth variation. And when it comes to CMP, again, this is a very difficult structure to get a plain finish, right? You will always end up with a dishing, right, because you have large metal outside the structure compared to on the structure, right? But when you have a uniformly distributed structure density, then it is much easier to handle the process, both in patterning and also CMP. And this is again an example of a CMP uniformity issue addressed here, where you take a structure that has a trench, right, and now when you fill it, you will end up with this dish, right? But this is a large open area, so this is not only dishing in this direction, you will also have a dish in this direction, right? So continuously you will have a boat like a structure, right? So you are going to have something like this, right? So you have lower etch depth here, sorry, high bowing here compared to this, right? So this becomes a reliability concern, and also you are going to make device or contact on top of this, then the contact becomes a difficult point here, right? So if you put oxide on top of it and then you want to etch it, you want to make sure it clears everything, but already you have a thickness variation because of this bow that you have, right? So another way of handling this is by using perforation. So perforation helps you in addressing this density issue. So this can be a few tens of microns. So let's say this is 100 micron by 150 micron, a pretty large feature, right? So where you will see this dishing. So what we do is, instead of using this flat open area, you can segment this, right? So you can, instead of having a fully open trench, you make this segmented trench, right? So the segmented trench, but they are all connected, right? So electrically they are connected. You see here, so this allows you to do the electrical connection. It's not just an isolated feature. So when you do this, your filling is going to be uniform. So you will not have any dishing in this case, right? So you can have very uniform filling, so that it becomes very reliable. And then you can also have a larger contact that allows you to make this further contacting or bumping or whatever you do pretty easy. So this is only a concern at higher metallization levels, right? So not at lower metal levels where your structures are much smaller, where instead of dishing you might have some erosion and so on. So when you have large open areas with metal fill or even dielectric fill, you see these kind of issues, right? So I'm just discussing case by case, but your problem could be slightly different. So you have a large open dielectric, right, that you are trying to do, or you have large metal opening that you are trying to get a uniform thickness, right? So these are all the ways that you can handle. So the next thing is about interconnect itself. We briefly introduced this earlier, but let's look at what is the problem here. So you normally do some contact like this, right? You have a single point contact, and then the important thing is to place these contacts right at the right clearance from the edge. But you may not have luxury to put these contacts where you want. You may not have enough clearance, right? The clearance that you require to get a reliable connection, you may not be able to do it. So in those instances, it will be very hard to place the contacts. So the alternate way of improving this yield of contacting yield is by doubling, right? So now I have double contact, right? So if one is misaligned, then I have another contact that will take over, and then which will give me the contact required. This also improves your conductivity, right? So you have two parallel paths, and then you should be able to pump in more current, and you should be able to do better contacting, right? So this is how one can improve contact reliability. As I mentioned, in some instances you may not be able to do multiple contacts, so then you just live with one, but make sure that your contact holes are reasonably spaced, and you have to live with that. But wherever you could add multiple contacts, we should exploit this so that you have a better yield, right? So these are all the few examples, right, that you can find in improving yield by understanding the process limitation and integration limitation. So DFM is all about interfacing design knowledge with process knowledge, right? So so as I mentioned even in my first lecture on DFM, So designer and the fabrication group, they are not separated anymore. They should work as a group so that the process team and the process integration team understands what the designer needs are, and the same way designer also understand what are all the limitation of any process is, and the challenges that we have in integration, and accordingly you can modify your structure and also alter some of the circuits that you are trying to realize. So at the end of the day, you yield the device or the circuit that you want, right? So that is the primary goal. And during this course, the designers are pushing the fabrication folks to improve their process and putting their process window to the test. And at the same time, designers are also pushed to think new ways, right, in order to improve yield by innovative design strategies, right, contacting strategies, and so on, in order to increase your yield, right? So DFM is something very important early on in your understanding. One should be aware of this. So one should not be isolate themselves from only design, not understanding how these devices are fabricated and what are all the limitations. So that will only result in miscommunication, and you won't be able to realize desired device and circuit. So I hope you appreciate the importance of understanding the process while also looking at new innovative design strategies to improve your yield and reliability of circuits and devices.